Hello students, hope you're doing well. Now let's move on to the next topic, that is simple harmonic motion. In this video, we'll be just discussing about the basics of simple harmonic motion. That is, we'll try to define what is simple harmonic motion. Then we'll try to give an equation of simple harmonic motion and try to understand it. Then the various parameters associated with simple harmonic motion, that is position or displacement, velocity of SHM, acceleration of SHM. These are the things that we are going to look at in this particular video. Now let's first define a simple harmonic motion. Now simple harmonic motion is first an oscillation, and I hope you know what is an oscillation. Any to and fro motion is called oscillation. So it's an oscillation. Now in this oscillation, if the acceleration is always directed towards the mean position, then that is called simple harmonic. Of course, one is acceleration should be directed towards the mean position. Next is acceleration should be proportional to the displacement from the mean position. Then it is simple harmonic motion. So what are the conditions for a motion to be simple harmonic? First, it should be oscillation. So I hope you know what is oscillation. Oscillation is a to and fro motion. Second, the acceleration should be proportional to displacement. Third, the acceleration should always be directed towards the mean position, that is negative. So if these three conditions are satisfied, then it is simple harmonic motion. Now if you look at these things, like if I'm talking about this oscillation, now this is moving like this. Now if you look at the force acting on it, force acting is spring force is given by kx. So acceleration can be written as kx by m. Now k is constant, m is constant, I see acceleration is proportional to x. So it is oscillation and acceleration is proportional to x. And the second part, now if you look at it, if I compress it, it will try to come back. If I elongate it, again it will try to come back. So the acceleration is always directed towards the mean position. So there is a negative sign. So this is SHM. Now similarly, if I take a simple pendulum with small displacement, if I draw a graph of it, I'll get something of this kind. So if these three conditions are satisfied, then I can say that simple harmonic motion is motion that is described by a sine or a cosine wave in position versus time. So if I draw a position time graph for that particular let's say motion, I would get either a sine graph or cosine graph. So that's what is the basic idea, basic definition of simple harmonic motion. And why do we call it simple harmonic motion? Possibly because acceleration is directly proportional to x. That is the simplest proportion that we can have. Maybe that's the reason why it is called simple harmonic motion. Now let's try to understand position of SHM at a given time. So in order to understand that, let's define a few things. I tried to draw a graph of a simple harmonic motion with respect to time. So that's why I'm getting a graph here. But actual motion would be something like this, goes like this on the same path, right? So because I'm drawing with respect to time, I'm getting this as a sine wave. Now this position is called mean position. These tips or the bottoms, these are all called extreme positions, right? So at any time, if I want to find, let's say y is the displacement of the particle at any time, because it is a sine wave, I can write y equal to a sine omega t. This is expression for SHM. And we write plus or minus phi to represent whether it is starting from mean position or not. Now because this is starting from mean position, from initial position, I can write it as a sine omega t, here phi would be equal to 0. Now let me take a situation something of this kind. It starts from here. So here initially what is phi? Phi is already 90 degrees. So in that case, for this I can write y equal to a sine omega t minus 90. If I'm taking this way, it will be minus 90. Because it is starting at this point. It is starting at this point, phi is minus 90. So there is an initial phase difference. So that's why we take this into consideration, or otherwise I can write it as a cos omega t. If it is starting at any other position, any other initial phase, then we call it as, then phi is not 0, and accordingly we write the expression for SHM. Now here let's look at various phases. Now if I take it as this would be 0, this would be pi by 2, this would be pi, this would be 3 pi by 2, this would be 2 pi, and so on. So these angular positions are called phase. Now let's say an SHM is starting from this point and initial phase is phi. Then my expression would be y equal to simply a sine omega t plus phi. Why? Where phi is the initial phase. So this is what is the equation for SHM or position of SHM. Now the other things that we have to see is omega. What is omega? Omega is written as 2 pi f, where f is the frequency, and this is called angular frequency. Right? So omega is given by 2 pi f and it is known as angular frequency. So position depends on the initial phase, angular frequency, and A. A is what? This A is amplitude. And what is amplitude? Amplitude is maximum displacement from mean position. Here this would be A. So what is amplitude? Amplitude is maximum displacement from mean position. It can be on either sides. It need not be only on positive or negative side. It can be on either side. So maximum displacement from mean position. So this is what is there about the equation of SHM, where I find the expression for position of SHM. Now let's look at various things here. Of course, we have graphs for everything. If I have an SHM starting from extreme position, then the graph is given by y equal to a cos omega t, right? You can see that graph is given by y equal to a cos omega t, or you can write sin omega t minus pi by 2, whichever. Now you can see that, from this figure, now as I'm going, I can find out what is the time period of SHM also. That we'll be discussing a little later. Now based on this expression, I can find out position of SHM at any time. Let's say time period of SHM is given by capital T. Now the question is, find position of SHM. Position of SHM I'll take starting from extreme position. If it is starting from extreme position, the equation would be a cos omega t. Extreme position at time, I'll say t by 6. I'll just write it as at time equal to t by 6, or 1/6 of the time period. So I'll write y equal to a cos omega. Omega is 2 pi by t. Into time is what? T by 6. So t cancels. I'll get y equal to a cos 2 pi by 3. Cos pi by 3 is cos 60, so it is a by 2. So this is the position of SHM at t equal to t by 6. Now let me do the same thing for an SHM starting from mean position. If SHM is starting from mean position, expression would be a sin omega t. In that case, y would be equal to a sin omega is 2 pi by t, where t is time period, into t by 6. So t cancels, so this becomes pi by 3. So a sin pi by 3 would be equal to root 3 by 2a. So you can see that there is a difference between them. So we have to be careful whether the SHM is starting from mean position or extreme position while using the formula for finding displacement or velocity or any other thing. After this, let's look at velocity of SHM. I'll take the same graph. So what is position? We are talking about an SHM starting from extreme position with zero phase. Y equal to a cos omega t. Then velocity can be written as dy by dt. So that can be written as a omega. Differentiation of cos omega t is minus sin omega t. Of course, omega into minus sin omega t, so omega comes out. So I'll get minus a omega sin omega t. Now you can see this is the graph for velocity for this particular one. This is the graph for position. This is graph for velocity. So this is how I find velocity of SHM at time t. Now I know I want to get it in terms of position. Now what is cos omega t here? Cos omega t equal to, I can write it as y by a. So if cos omega t is y by a, I can write sin omega t equal to under root of 1 minus cos square omega t. So that can be written as 1 minus y square by a square, or that is under root of a square minus y square by a square. This is what is sin omega t. Let me put it here. Then I'll get v equal to minus a omega into root over a square minus y square. If I take out this a, it comes outside. So velocity at a given time. So at a given position y is given by minus omega into root over a square minus y square. So this is the other way of finding velocity of SHM. Now, not the other way. This is velocity as a function of time and this is velocity as a function of position. Now at mean position, what is y? Y is 0. So at mean position, I can say velocity is omega into a. Omega, that is the maximum velocity that we can have. At extreme position, y equal to a, so this becomes velocity would be 0. So a particle would be at rest momentarily at extreme position and it will have a maximum velocity at mean position. So in this way we can find velocity of SHM. Then we have acceleration of SHM. We'll continue with the same expression. We got displacement as a cos omega t. When we differentiated it, we got v equal to minus a omega sine omega t. So acceleration is how much? It is dv by dt. So that is equal to minus a omega, right? Write it like this. Sine omega t is what? Sine omega t is differentiation of sine omega t is omega into cos omega t. So that can be written as minus a omega square into cos omega t. Or this can be written as minus omega square into a cos omega t. Now a cos omega t is y. So we have acceleration equal to minus omega square y. Now omega is angular frequency, that is constant. So I have acceleration proportional to minus y. That's what is the basic condition necessary for SHM. So I can directly use this expression if I know angular frequency. Otherwise, I can just use the ratio proportion. And if you look at the graph, we'll get a graph something of this kind for acceleration of SHM, right? So after that, let's try to get expression for time period of SHM. So we had got the expression a equal to minus omega square x or y, where x or y is the displacement from mean position. Now we have f, so omega, if I write force equal to F equal to, I can write kx minus kx. This is the restoring force. Now what is restoring force? A force which always tries to bring a particle back to its original position is called restoring force. Now from this F equal to ma, I can write ma equal to minus kx or a equal to minus k by m into x. I'll call this equation as 1 and this is 2. From these two I have omega square equal to k by m, or I have omega equal to root k by m. Now omega can be written as omega can be written as 2 pi by t. So we have 2 pi by t equal to root k by m, or from this we have t equal to 2 pi root m by k. Now so that means if force can be expressed as kx, then the time period of SHM is given by t equal to 2 pi root m by k, where k is force constant. In this way, if I can find the coefficient of x in the expression for force, I can find what is the time period of oscillation. Now this is one thing, and there are cases where we can directly relate the time period and find how much is the time period or the time taken for a particular part of the journey. Now for example, let's say I take an SHM. SHM starts from mean position, goes to extreme position, comes back and goes here and comes back. Now the total time taken is how much? T. So time taken to go from mean position to extreme position is t by 4. Again coming back is t by 4. Similarly here also going is t by 4 and coming back is t by 4. This is how it is separated. Now if I want to find time taken by a particle from mean position to extreme position, so how do I do it? So if an SHM is starting from mean position, then expression is given by y equal to a sine omega t. I want to find time taken to go to a by 2, let's say half the amplitude. So I'll write a by 2 equal to a sine omega into t. So a cancels. So I have sine omega t is half, or I can write omega t is 30 degrees, which is pi by 6. Now omega is how much? 2 pi by t into t equal to pi by 6. From this, what I'll cancel this pi, I'll get t equal to t by 12. That means time taken to go from mean position to, I'll say 0 to a by 2 is how much? I'll take a different color. So 0 to a by 2 is t by 12. 0 to a is how much? T by 4. So a by 2 to a would be t by 4 minus t by 12, that is equal to t by 6. So if you can remember these things, these results will also be helpful for solving the questions. So let's have a quick look of what all things we have done. We have defined what is an SHM, the condition necessary for SHM. An SHM is any oscillation in which acceleration is directly proportional to displacement from the main position and is always directed towards the main position. And any sine or cosine wave represent SHM if it is a representation of position of SHM with respect to time. Then we got expressions for velocity as a function of time as well as velocity as a function of position. And then we found expression for acceleration and then finally expression for time period. So this is what is there about the definition of SHM and how finding time period, acceleration, velocity and position of SHM if the equation is given. Hope you could follow this. Thank you very much and keep watching all other videos of Get My Class where we have videos on various other concepts and also solutions to different levels of question as per your competitive exams. Thank you very much once again.